All right, cycloalkanes. So a cycloalkane, for example, let's say we have you guys know hexane, one, two, three, four, five, six, right? This would be hexane, which has a formula of C6H14. If you were to take and tether, if you were to tie this carbon over to this carbon like this, okay, then you'd end up with a ring of carbons, okay? And this is what we call cyclohexane. And it would have a formula of C6H12, right? Because when you tie these two carbons together, you lose two hydrogens in the process. So that's one example of a cycloalkane. Okay, so as I just stated, a cycloalkane is an alkane, right? Comprised of only carbon and hydrogen, in which the carbon atoms form a ring. And unlike an alkane, which has the formula CnH2n plus 2, a cycloalkane has the formula CnH2n because we have one less hydrogen when we make our ring. You see here the structure of cholesterol, which is an example of a biomolecule that has several cycloalkanes, right? You can see you've got a ring here, then we have another ring here, there's another, there's two more, right? There's one here. Those are all six-membered rings. And then you have a ring with five carbons in it like that. So cycloalkanes very important in biochemistry. All right, and on the first slide, I showed you the structure of cyclohexanes. You can imagine if you have five carbons in a ring, that would be cyclopentane. Four carbons in a ring is cyclobutane, and three carbons in a ring is cyclopropane. And so the formula for cyclopropane is going to be C3H6. For cyclobutane, it'd be C4H8. For cyclopentane, it would be C5H10, and then for cyclohexane, as we saw, it would be C6H12. And you can see the condensed structures here, and you can also see the skeletal representations, which I refer to as bond line structures, okay? And it's actually kind of fun to make models of these molecules because you'll see once you get to cyclohexane, it's the only cycloalkane where all of the carbons are perfectly tetrahedral. Tetrahedral. They're all perfectly tetrahedral, and they all have that bond angle of 109.5 degrees that we see in the tetrahedron. And so that's what makes cyclohexane so important to us as chemists. So when we want to name a cycloalkane, we're going to follow the rules that are shown here. So according to the International Union of Pure and Applied Chemistry rules, cycloalkanes are named by placing the prefix cyclo before the name. So cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, cyclooctane, so on and so forth. When substituted cyclohexanes are named, the position of a single attached group does not need to be specified in the name. So if you take a look at this example here, okay, there's only one substituent on the cyclopentane ring, so we just call it one. Sorry, we call it methyl cyclopentane. If you were to call it one methyl cyclopentane, that would be redundant because there's only one substituent on there anyway. Once you get two or more groups attached to your cycloalkane, that's when you have to start putting in numbers, right? Because here you have 1,2-dimethyl cyclopentane. And again, you want to give them the lowest possible numbers. So you're going to go clockwise in this case, going from 1 to 2. But why would you need numbers? Because what if you had this molecule like this? That would be 1,3-dimethyl cyclopentane. And so numbering becomes important when we have two or more substituents. Now, if you take a look at the last example that's shown here, where we have two different substituents, well, in that case, what we have to do is we're going to number chlorine as being the first substituent because C for chloro comes in the alphabet before M for methyl. So we'd call this 1-chloro 2, or sorry, 1-chloro 3-methyl cyclopentane, like that. Okay, so you're gonna have to practice these in order to get really good at them. So make sure you're going over the practice problems in the textbook. All right, so let's see if we could name this cycloalkane. You can see that it is a cyclohexane because we have six carbons in the ring. We have two methyl groups, so we're going to start here. 1, 2, 3. We want to give them the lowest possible number, so that's why we wouldn't go 1, 2, 3, 4, 5, because then we'd have 1 and 5 versus 1 and 3. Well, what's a lower number, 5 or 3, right? The answer is 3, and so we're going to erase all this junk here, okay? I'll put my 1 back here. And so we would call this compound 1,3. Now there's two methyls, so dimethyl, I can do it here, dimethyl cyclohexane, like that. All right, now what about stereoisomers? If you take advanced organic chemistry, you'll do a whole chapter in stereoisomers, but we just kind of scratched the surface in this class. And it says here the lack of free rotation around carbon-carbon bonds in a cycloalkane leads to an extremely important kind of isomerism called stereoisomerism. And stereoisomers are compounds with the same structural formula, but different spatial arrangements of the atoms. So it means the atoms are arranged in a different way in space. And two types of stereoisomerism are going to be cis and trans stereoisomerism. Now, cis means you have two groups that are attached on the same side of the molecule, and it's usually going to be a cycloalkane in this class. And trans means you're going to have two groups on opposite sides of the cycloalkane in this chapter. And so if you take a look at 1,2-dimethyl cyclopentane, right, if we were to just draw 1,2-dimethyl cyclopentane, we draw a cyclopentane, and then we go 1, 2, like this. However, the methyl groups, both of them could be on the same side, like you see here, they're both at the bottom part of the molecule, and we would call that the cis 1,2-dimethyl cyclohexane, or they could be on opposite sides. You see one is up and one is down. We would call that the trans 1,2-dimethyl cyclopentane. So keep in mind, these are different compounds. They're going to have different melting points, different boiling points, different densities, and all that kind of things. And so um, we get these two distinct stereoisomers, and so you have to be able to identify cis when the two groups are on the same side of the molecule, or trans when they're on opposite sides of the molecule. So it says here, draw the skeletal structures of the isomers of 1,3-dimethylcyclobutane. Indicate which ones are cis-trans isomers. So if we draw cyclobutane, so this would be cyclobutane like this, okay? Well, it says here 1, 3. So we could have the two methyl groups on the same side. And instead of using what we saw in the previous slide, which we call Haworth projection, I'm going to use a wedge like this to mean that the methyl group is going up. Okay, so if I use a shaded in wedge like this means it's coming up. And if I use a dash like this, it means it's going down into the page, okay? So if I have one methyl group going up like this and one going up like this would be cis 1,3-dimethyl cyclobutane, okay? Now for the other stereoisomer, I'm just going to copy and paste this and move it over here. I'll put this here like this. We'll change the color, okay? So if I have this molecule, now what I'm going to do is I'm going to remove this wedge and I'm going to change it to a dash. Okay, so if I change this to a dash, come on, where's my black pen? There we go. Oops. I meant a dash and I started drawing a wedge. What am I doing? There we go. Okay. Well, now you can see that this methyl group is going down. Okay. And again, we call this a dash. This one is coming up. And again, we call this a wedge. So one's up, one's down. Therefore, they're on opposite sides of the molecule. So we would call this trans 1,3-dimethyl cyclobutane. Now, sometimes students will email me and they'll ask me, yeah, but what if you had this where you had one methyl group going down like this and one methyl group going down like this? Okay. This molecule that I've just drawn is going to be identical to this one, right? Because the two methyl groups are cis to each other, and so there's no difference. So these would be the two stereoisomers of 1,3-dimethyl cyclobutane. You have the cis 1,3-dimethyl cyclobutane, where the two methyl groups are both pointing up, or they could both be pointing down. Either way, it would be the same thing. And then you have a situation where they're trans to each other. One is down and one is up. Now, if you're wondering, oh boy, I'm getting frustrated by this stereoisomerism, why do I have to study this? Why should I even care about this? Well, there's a good reason, many, many good reasons. But I'm sure some of you have heard of the drug thalidomide, which was prescribed to pregnant females in the 1960s to alleviate morning sickness in the first trimester. And the problem with thalidomide is that you have a bond in here that can be either a dash or a wedge. And they sold it or they marketed it and administered it to patients as a 50-50 mixture where the bond was up and the bond was down. And so 50% of the sample was the good drug, the thalidomide, that alleviated the morning sickness, but the other half was the stereoisomer that was a teratogen. Okay, and a teratogen just means it mutates the fetus, and so it led to the birth of many babies that were born with severe disabilities, and most of them died. So anyhow, so thalidomide is still a marketed drug. However, now it's only marketed as a single stereoisomer. It's what we call an enantiomer, and I'm not going to get into that right now, but that's why stereoisomerism is so important to us as chemists.